Okay, so my name is Dimitris Tsapetis. I'm a postdoctoral research fellow at Hopkins University, and I'm doing research on uncertainty quantification, as I mentioned before, on material science and extreme environments. And then I'm also one of the lead developers of our in-house library, UQPy, which stands for Uncertainty Quantification with Python. So let me introduce you to our library. UQPy is a collection of Python modules that address various fields of the uncertainty quantification, um, starting from simple forward propagation, inverse, surrogates, even dimensionality reduction, and more novel methods that are developed in our group. It includes simple applied methods, for example, Monte Carlo sampling, which is a method widely used, but our goal is to make UQPy a comprehensive library that includes both simple methods for researchers out there and also state-of-the-art methods that are developed inside our group. So UQPy serves both as a UQ toolbox, which is really easy to use for researchers, as well as a development environment where they can easily prototype solutions, UQ solutions, and use them for their own research. And we are really proud that with the latest update of UQPy, we were able to have contributions from researchers from all around the world, even from companies like Siemens, as you can see here, or universities from Nevada or Czech Republic, Germany. And our latest effort is focused on integrating UQPy with the Natural Hazard Center, or NERI, at Berkeley, and plugging in UQPy as one of the default tools there. So UQPy is version controlled and is available in our GitHub repository. Version 4.15 is available, and you can download it either from as a Python package or an Anaconda source. Here you can see the QR code, which if you scan it will take you directly to our documentation, which is extensive, includes both theory, documentation, and examples for our code. Or you can also reference our papers from the Journal of Computational Science that includes the basic architecture of UQPy, as well as the paper for the latest version, version 4, which was released only a few weeks ago, and includes our latest developments. So let me start with mentioning what changed from the previous version, version 3 to version 4. Until now, UQPy was a library developed in an academic environment. So we made an effort on taking that library, refactoring and restructuring it to follow the modern software development practices and make it as user-friendly and robust as possible and give it to the scientific community out there. So let me start with that. We restructured UQPy to conform with the latest Python coding conventions, from naming to class and file conventions. Then we refactored it. So we had previously a really tightly coupled features that we are now made independent of each other, and they can be joined with different pieces of the software, making it much more user-friendly and prototyping much more, let's say, much faster. So apart from improving accessibility and modularity of the software, we wanted also to improve the whole software development lifecycle. That's why we introduced a proper way of doing software development, which is introducing GitHub workflow for integrating changes, as well as a whole DevOps environment. This environment contains continuous integration, automated testing to ensure robustness of the software, as well as continuous delivery to reduce the overhead of our developers, and also providing UQPy via several channels such as PyPy, as I mentioned before, Conda, and even Docker images, so you can be independent of the operating system. The Git flow, as I mentioned before, that we used as our branching strategy, we have one master branch with the latest stable version, The development version has all the latest functionality and fixes to be merged shortly, and we work on feature branches or bug fix branches to develop our code. Let me switch now to the continuous integration practice that we used. To ensure robustness of the software, as I mentioned before, we implemented unit testing throughout our code. So now all our functionalities are tested to achieve a minimum of 80% coverage, and that's not only for vanilla cases, but edge cases that we find and we know from benchmark examples in the literature. We used one of the tools out there, the most well-known ones, Azure Pipelines, to automate the whole process, run tests for commits, pull requests, ensure the code quality of the code using Pylint, and making sure that our code has, of course, no bugs with auto detection tools and code quality check tools like Sonar Cloud. From the continuous development perspective, UQPy is automatically versioned now using a tool called Git version, which traverses the Git tree and generate the code for us, generate the code version for us. We automated the release from GitHub releases, Python packages, as well as a Docker image. And as I mentioned before, we have our documentation now, which is a documentation as a code. It always reflects the latest version and includes examples that can be opened directly to a binder link and run when the user wants without having to install all the dependencies. As far as UQPy architecture is concerned, we have refactored it, as I mentioned before, to make it as object-oriented and modularized as possible, to allow for easy extension. UQPy has 11 distinct modules. At the base lie distributions and run model modules, and that support all of the rest. You can see here the most advanced modules in the middle, from dimension reduction, reliability, sensitivity, and surrogates, and some auxiliary packages such as the transformation and utilities that provide methods used throughout our code. So here you can see a high-level architecture of the code and all the functionalities included in UQPy. Again, you can see that supportive are the distributions and the utilities, and at our core lies the run model module, which it will be the last thing that we'll mention here in this presentation, which also now has a Bridge plugin. And we use this model propagation tool to interface with all other capabilities. Let me give you an example of how our UQPy library has been refactored. Now we use abstract-based classes and subclasses to create and extend our UQ methods. For example, the sampling module has some classes, as you can see below, the adaptive rigging, importance sampling, Monte Carlo sampling. All these are independent classes that we can use and are readily available, but we have some like MCMC and Stratified, which provide the interface for users to create their own methods. So in case of MCMC, we can create new ones via subclassing, and the way we do that is we have, as I mentioned before, the MCMC class that we extend, and we can provide custom implementations. So adding a new subclass is really straightforward, not only for the sampling, but any module. But in the case of MCMC, what we need to do is create a subclass, a child class of the MCMC method, only override one of the functions here, which is the run one iteration. So the run one iteration method defines how we will propagate to the next Markov chain sample. And by doing so, we can have complete access to all the existing attributes and data of the base class and automatically have our own new implementation ready. More details on that, on the MCMC and all other classes and how to extend it, can be found, again, in our documentation. So here you can see the overall structure of an example here, the sampling module, where the independent classes are shown in the cyan, and the darker blue are the abstract classes with their own custom implementations. We have followed a similar pattern throughout our code. For example, here you can see the distributions model, which has base classes for continuous 1D distribution, discrete 1D, and multivariate distributions. Also includes copulas and a collection of independent distributions. It is consistent with the distribution packets in SciPy stats, and we have adopted an object-oriented architecture so that we can easily extend it. 18 continuous 1D and discrete two discrete distributions are available, and we can always create multivariate distributions by combining independent marginals and copulas. Let's switch to some modules of UQPy that have been written from scratch, from version 3 to version 4, to improve performance and also make them more user-friendly. One of them is the dimension reduction module, where we have, again, you can see one abstract class for the POD method with two concrete implementations of direct and snapshot POD, and more advanced methods such as diffusion maps for dimensionality reduction and projection also to Grassmann manifolds that can be coupled with diffusion maps as well. Another module that has been refactored is the surrogate module. So we have written the Gaussian process regression from scratch. Abstract classes are now available for both regression methods and kernels. So you can see a few methods available, but in our documentation, we have detailed process on how to extend that and create your new regression or new kernels. We have also added the constraints, which implement the virtual point method and allows us to impose physical constraints on these surrogates. And in a similar fashion, we have refactored polynomial chaos expansion. We support two polynomials, Hermite and Alexander. Again, really easy to extend right here. These two polynomials can be coupled and create a polynomial basis with naive tensor product basis or the much more advanced hyperbolic truncation, and regression methods that include a simple lasso or least square regression, and two, the most advanced least angle regression. So here I should mention also that a novel method is added, which is the physics constraint PCE. It was only presented a few months ago. You can find more details about how a physics PCE works in this archive link, and it's already integrated into UQPy if you want to use it and examples to see how it works. Another module that also has been extended since version 3 is the sensitivity module. Initially, we only had the Morse sensitivity. Now, because of how UQPy has been restructured to version 4, we have a contribution from TU Braunschweig with several sensitivity methods that have been added, from simple Sobol to Chatterjee indices, grammar for Mises indices. And also we have polynomial chaos sensitivity included by our own group, and more methods to come with adaptive Sobol indices based on Gaussian processes. And so last but not least, I want to mention Run model, which is our way of interfacing with other software and how we execute our models. So Run model is our class that's dedicated to the execution of computational models. And depending on the type of the model, until now, we could only interface with Python models or any third-party model. So the third-party model we could interface with could be any Blacks model that work with ASCII-based text file. So we could also designate if we want to run our model evaluations in serial or in parallel. We could run both Python and third-party software in parallel in our laptops when we depend if we have OpenMPI installed or in a cluster. And also we have a more designated cluster execution setting by setting one of our attributes in the run model method, which requires an additional cluster script, which the role of the script is to orchestrate the runs between the nodes in the cores. So let me talk with a bit more detail of what each one of the models does. For example, the Python model, we only need one Python file that contains the way we which evaluate our model. You can see here the only information is needed is the name of the Python file, as well as the function that contains the model evaluation. We can plug it into our run model, which takes care of the execution either locally or in a cluster. And then we provide our samples to forward propagate our model. In the case of the third-party model, again, remind you, it can be any model and which we treat as a black box. We need to interface with the input file, which is our input template file. You can see there are two parameters that are related to our input file, which is the name of the file and parameters that we want to replace. So what the third-party model does is searches for the parameter X, replaces it, and then the model script below takes care of the execution. And finally, we process the output. The interface will be the same, plug our third-party model into run model, provide the samples, and it will take care of running the model. But again, these two previous solutions take into account that you have all the dependencies locally on your machine, either your laptop, your PC, or your cluster. And that's one reason that we have moved forward with Ambridge model, where we can have all of our dependencies in one Docker container. What we do now is we provide just a link where we can interface with our Docker using the Ambridge patterns and providing the URL link. Again, the only thing we have to do is plug that model inside the run model, which takes care of the execution, provide the samples, and we can retrieve the quantities of interest after the evaluation of our model. So here I should mention that we only recently, 2 weeks ago, started decoupling with UMBridge model, and I was able to run both with Python, and by combining our third-party model evaluation and the Ambridge, also run it with an Octave model that runs on a Docker container. And with that, I would like to summarize. So the UQPy has seen an extensive development, and we have refactored and restructured that from the previous version to the current one, adopted modern continuous integration, testing, and deployment strategies to reduce the overhead of our developers and make sure that our software is robust. Also, we have, with the whole DevOps patterns that we follow, we have improved the development and allowed external contributors to our project. And we have focused on continuing to improve and advance our UQ capabilities and introducing any new novel methods that are introduced by our group. So finally, I would like to acknowledge all the contributions of our team, as well as our external contributors from universities and companies throughout the world, and our funding resources from ARL, DOE, DETRA, and NSF that had supported and funded the development of this software. And with that, I will conclude my presentation, and I'm open to any questions.